So we said in this video we are going to discuss something called the confusion matrix, right? Confusion matrix. Confusion matrix. For our classifiers, just like our LDA or logistic regression or things like that, right? Our classifiers, they make two fundamental types of errors. So there are two types of errors. Let me write two types of errors. So our types of errors, number one is, let's say we're talking about people defaulting on their loan, for example, to just make this concrete, right? Defaulting on loan or paying credit, their credit card balance or whatever it is, right? So we're talking about defaulting. So defaulting, it's either a person is going to default or a person is not going to default, right? Yes or no. So type number one is when you classify someone, error number one is you're going to assign person who defaulted to the no default class. That is an error, right? No default class. This person has defaulted. So we assigned a person who defaulted to the no default class. We made a mistake there, right? And then error number two, we are going to assign, let's say our prediction is assigned person who does not default to the default class. We've made an error again, right? Our classifier has made an error because this person did not default, but then our predictor said they defaulted. So we've made an error, we've made a mistake. So which means these are the two fundamental types of errors that classifiers make, right? Our classifiers, like our LDA here, they make these two fundamental errors. So as a company or as an individual, you might be interested in knowing which type of error is being made by your classifier. And this is where the confusion matrix helps you to figure it out, right? Let's look at if we run our LDA. When we run our LDA, let's say we run our LDA on default data for 10,000 individuals in our training set, right? So we have 10,000 individuals in our training set, and then we run our LDA and we look at the results. When we look at the results, what did we predict for those 10,000 people? They're in the training set, so we already know their true value. Did they default or not? And then we compare with the prediction. It's like putting in a matrix, let's say we put in Excel or whatever it is. We have all their variables, right? And then here we say, what is their true state? Did they default or not? And then here we add a column of our prediction. What was our prediction, right? What was our prediction for those people? And we create a confusion matrix. This confusion matrix is created this way, right? Here you have true default status. We're going to have true default status. And then here we're going to have our predicted default status, right? So our true default status will either be a yes or a no, right? And our predicted default status, we may predict that the person yes defaulted, or we predict that they didn't default. Let's just add a total column here, and we are going to add a total row here. So we create a table that is like this. We create a table like this. Yeah, perfect. Yeah, a table like that, right? Let's just put in some values that we got when we ran our script and we ran our LDA and stuff like that. Let's say on those 10,000 people that we got, right? For people let's write it this way. What did our LDA predict? Our LDA predicted a yes. It predicted a yes for how many people? It predicted a yes for 104 people, right? And now it predicted a no for 9896 people. The total here is going to be 10,000. 10,000 people, right? Let's look at our data set. When we look at our data set, our training data set, how many were true default status equal to yes? The total for them was 333. Cool. And then the status for no. The status for no was 9667. Perfect. So how do we fill in these 1, 2, 3, 4 boxes here? This is what we do. We look at our columns here, and then we say this column was predicted to be yes, but was it a true yes? Did the data also say it was originally a yes? So we want to count how many people we predicted yeses for who were really yeses. You get what I mean? Who were true yeses. So if our predicted was a yes, and then our true was also a yes, these are the number of people that we put here. And let's say we have 81 people. So we have 81 people that were really yeses, that were predicted to be yeses, and they were really, really yeses as well. They defaulted, right? So we predicted correctly here. We predicted that they are going to default, and they actually did default. Cool. And then here, there are some people that will say, this person defaulted, but in actuality, they didn't. So the people in this box here, we predicted that they are going to default, but they actually didn't default. So let's say those people are 23 people. Cool. Same happens here. There are some people who are going to say, no, this person I predict that is not going to default. Our LDA is going to predict that they are not going to default, but actually they did default. They're going to be in this box here. So predicted no, true yes, they're going to be here. Let's say, so there are 252 people. And then here, there are going to be people who are going to, our LDA is going to predict that they didn't default, and actually they also didn't default. They're going to be in this box here. So it's going to be 9,644 people. Basically, that is the confusion matrix. That's what a confusion matrix is, right? So let's see how it allows us to really know what errors our LDA is doing. As you can see here, there are a total of 104. Let me use a different color so you can see when I highlight. So there are a total of 104 people. There are a total of 104 people who were predicted to default. Prediction was yes. The total was 104. They were predicted to default according to our LDA, right? Of these 104, we see that 81 actually defaulted. 81 actually defaulted, and 23 did not default, right? So for our prediction, we predicted 104 are going to default. And then we go a step further. We're like, okay, for those people that we predicted that they're going to default, how many actually defaulted in our training data set? 81 did, and 23 did not, right? So we are saying in our training data set, right? Training data set, here we're saying 23. We are predicting. Imagine we are just predicting. We're like, we predicted 23 did not default. 23 did not default, right? We predicted 23. We predicted that 23 are going to default, but their true status is a no. It means for the people that were truly defaulting, how many did we take away from their true status? For people who were truly defaulting. This is the column for people who were truly defaulting. The true defaulters. Our prediction said yes. So we basically took away 23 people. 23 people from the actual that they were supposed to be. They were supposed to be no's. But our prediction gave them a yes. So from this default set, we took away 23 people and gave them the wrong default state. 23 out of this no set. So which means it means only 23 out of all defaulters, 9667, the total of all defaulters, or the total that had no default. If I'm getting this mixed up, I think for the past minute or something I've been getting it mixed up. So for the people who did not default, we blamed them. These 23, we blamed 23, and our LDA blamed them, said, you guys defaulted. I'm predicting that you are going to default. So our LDA lied for 23 people. 23 innocent people. And how many innocent people did we have? We had 9667. We had 9667 were innocent. They didn't default. But we predicted 23 of them to default. So we took 23 and we blamed 23 wrongly. So only 23 out of 9667 who didn't default. So these guys who didn't default were incorrectly labeled. I think you agree with me here. They were incorrectly labeled. They are no's, but our LDA put them under yes. Our LDM put them under yes, which was wrong, right? And this if you calculate, it's going to be a very, very low error rate. You'll be like, oh, that's a good error rate, right? That's a good error rate. But now let's look at people who actually did default. There are people who really, really defaulted. These ones here, according to our true, this is the true column, right? This total here, these guys, they really, really defaulted in our training data set. We know that these 333 people, 333 people, they really defaulted. We know that. So, but what is our predictor doing? It said, yes, I predict for 81. And then it said no for 252. So for the people who defaulted, we had the yes default. Our predictor was wrong 252 times, or for 252 of them. That's a large number, because it means 252 over 333 were incorrectly predicted to not default when they actually did. You see here, they are in the actual column for actual defaulters, right? But our prediction is saying no. Our LDA is saying no for 252. That is close to 75.7% error. This is very fascinating. For the people who didn't default, we had a very, very, very small error. We were mostly accurate. But then for those who defaulted, who really did default, we couldn't pick them up. We missed so many people. Our LDA missed so many of the defaulters. Right? If we run this LDA and you look at the overall error rate, the overall error rate is going to be something close to 3. It's going to be something like 2.75. That is the overall error rate of our LDA. That is going to be the overall error rate that is going to be given out by let's say a programming like R, right? And this brings about a very, very, very important point, right? A very important point. Many people that I have interacted with, they look at this overall error rate, and then they are happy. They are like 2.75 error rate. That is fine. Let's put that into production. Our LDA works. It gets 2.5% correct. But that is the overall or total error rate, right? It is the total error rate. But when you look at the specific classes themselves, the no class, the true no class, what is the error rate for the true no class for our predictor? Our predictor is going to, for the no class, is going to do very well. It's doing extremely well on our no class. But then for the yes class, for people who really predicted, we are not going to pick up many of them. We're going to have a high error rate. So here there is class specific errors. There are class specific errors, right? And now a credit card company, it might be trying to identify high risk individuals, right? high-risk individuals. How do you identify high-risk individuals? You want to concentrate on how well am I predicting this year's class. That's how you what? You identify high-risk individuals, right? How well am I predicting this year's class? And if you're someone who works for a credit card company, and you just look at the overall error rate, you're going to miss this hidden class error here. You're going to miss this 75% error. That is a that is a huge error. It is a high error, I would say. It's a high error rate, right? So you might have to dig deep into your errors, like into your classes. And your confusion matrix allows you to see that. It allows you to see those class errors. Otherwise, if it just spits this total overall error, you might miss those things. You might miss the class specific errors. And this also applies to medicine and in biology, where something called sensitivity and specificity are important. Let's discuss those two terms. So, when we are looking at usually when we're looking at the performance of a classifier, we are going to look at something called sensitivity, right? And specificity. So sensitivity is defined as the true defaulters, in our case here, true defaulters that are identified as defaulters. So here we are looking at true defaulters that are identified as defaulters. Cool. So here, these are the true defaulters, right? This column here, this first column, these are the true defaulters. And we want to know our sensitivity. So true defaulters that are identified, which means is this 81, is the yes and the yes. The yes, true defaulters, and we predicted them to be true defaulters as well. So cool, we predicted them to be defaulters. So our sensitivity in this case is going to be 81 over 333, which is approximately 24.3% here. Cool. And then we have something called the specificity. The specificity, it is the percentage of non-defaulters that are correctly identified. So in our case here, we're looking at defaulters, right? So specificity is going to be in percentage of non-defaulters that are going to be identified. Let's look at our non-defaulters. The second column is going to be non-defaulters, right? So how many were correctly identified as non-defaulters? It is the no. See this no here, 9644. So cool. It's going to be equal to 9644 over 9667, which is equal to 99. It's 99. I thought it was 98. 99.8%. 99.8%. Something like that, right? So sensitivity or classifying customers who default correctly is so low because our LDA here, our LDA estimate. Let's look at our LDA estimate. Why is it not doing a good job at identifying true defaulters? That's basically the question. When you say why is our sensitivity low, you're basically saying why aren't we catching many of these true defaulters? Why are we missing them? Right? Why are we missing them? That is the question that we want to ask here. It is because our LDA, it estimates the Bayes classifier, if you remember. Our LDA is just an estimate of the Bayes classifier. The Bayes classifier, it has the Bayes classifier, the Bayes classifier, it has the lowest total error rate. It is the lowest total error. I'm highlighting total because you remember here what happens here with our total. Our total could be low, but class specific could be high, right? The Bayes classifier just looks at the total error rate, not the class one. It doesn't look at the class ones. It looks at the total error rate, and it is the lowest total error rate. So it does not care about the class errors where this total is coming from. It does not care about each individual. This one could be 99, this one could be minus, no, not minus. This one could be 99, the other one could be 0.0000007. The total one could be 0.1. That's all Bayes cares about. That's 0.1. It doesn't care that the other one is 99, the other one is just like in our case here. This LDA, this was the LDA total error rate. LDA, which is an estimate of Bayes. Bayes is happy with this 2.75, right? Is happy with that. So that is a huge problem. Let's say for a credit company, because a credit company might be particularly interested or might particularly wish to avoid incorrectly classifying an individual. So it might be let me put a different column. So a credit card company might say, okay guys, let's sit down. When they sit down, they'll be like, which error has the most impact on our bottom line, right? A credit card company might then be more interested in avoiding incorrectly classifying an individual who will default, who is in this yes. So they're mostly interested in not wrongly classifying someone who is in this column. That's mostly what they're interested in, right? If they classify someone, who will not default, it is probably not less problematic, because if we misclassify someone who's not going to default and we predict that they are going to default, at the end of the day, it's not going to have much impact on our company, because at the end of the day, the person is not going to default. They are going to pay us. We'll be like, okay, it was just an error, but we have our money still. You get? But then if we do give money to someone who's going to default and we say they are not going to default, you see this 252, we could have gone and given them money, but at the end of the period, they don't give us our money. An error rate of 75%. That is large. That is large in that specific class. So when you sit in a credit card company, they might not be interested in the total error rate. It is interesting, yes, but the class specific one might be of more interest, because maybe misclassifying in this class will not have as much impact as misclassifying a person in this class on our bottom line. Because if we misclassify, if the person will not default is a no, and then we misclassified, like this 23 that we said, this 23, we misclassified them, we said they are going to default, but they actually didn't default. How's that going to affect our company? It's not going to, because this 23, in real life, they didn't default, they gave us our money. So these 23 are not harmful to us. But then misclassifying this 252 is very harmful, because we predicted them to be non-defaulters and we happily gave them the money. But then when reality hit, they were actually defaulters. So the credit card company might say, okay, the total takes into account all classes, but let's dig deeper into the class that really affects us. So that is why class performance is very, very, very important. You need to know the domain where you're working in. Are you in the medical field? Are you in the financial sector? Are you where? And what factors affect your bottom line? What factors are very important that you want your machine learning algorithm to perform best in? In our case here, the critical company, we want it to be very, very good at telling us who's going to default, because we want to avoid this situation, right? So the Bayes one, so they are just rubbing that to just discuss what someone can do, because now we are stuck with an LDA that is not performing well. How do we improve our LDA? That will be a person's question now. The person would then say, okay guys, what we can do is, what happens with Bayes classifier, it works by assigning an observation to the class for which, let's say PR of default equal to yes, given this observation is greater than 0.5. Let's say in a 2, like our case that we had here, in a binary classification like our yes and no, right? In a binary classification situation. So the threshold is what? 0.5. It's going to predict the default equal to yes if the probability is greater than 0.5, right? Cool. So just like bears, LDA will by default, because LDA tries by all means to estimate the bears, right? So by default, LDA uses that threshold. LDA uses 0.5 probability as the threshold, or 50%. That's what it uses. If someone is greater than 50%, it would predict a default of equal to yes, right? So what you can do is you can change this threshold, because if you're a company, if you're a credit company, because you have domain knowledge, you might be comfortable to say, I'm going to predict my default equal to yes for this observation if it is a probability greater than 0.2, probability of default greater than 0.2, right? That's what you might do. You might say, nah, okay, cool. Now that I know exactly what my aim is. For some people, they'll be like, guys, we want to be very conservative. If someone just gets a probability greater than 0.2, let's call them defaulters. We want to be very conservative here. We need to be very careful. We are a highly regulated industry in the financial sector, whatever our credit company, highly regulated. We do not want to play with these guys. If you just have a probability greater than 0.2, we are calling you a defaulter. That's what the company might say, right? So you change the what? You might change this threshold here from 0.5, the default, to that 0.2. Now what happens? Let's discuss what will happen in that case. If we change to 0.2 in our case and we run our LDA again, this is the matrix that is going to this is the matrix that was, sorry, I'm rushing because I don't want the video to be too long. Okay, need another line here. Cool. So this is what we're going to have. For our yes, we're going to have 195, and here we're going to have 138, and here still 333 people. And then here our no is going to change to 235, and then here it's going to be 9432, and then here it's still 9667. These are the 10,000 people that we had, and 9570, and then here it's now 430. Cool. This is the result of changing the threshold to 0.2. Cool. Now LDA predicts that 430 individuals, LDA is going to predict that 430 individuals are going to default, and then this 9,500 are not going to default. Cool. Of the 333 people, you see, of the 333 people that actually defaulted, we are now incorrectly assigning only 138 compared to before. Before we changed our threshold, we had 252 here. Now we have 138. So our error rate is changed to the error rate that is of concern to our bottom line. The error rate that is of concern to our bottom line is 138 divided by 333, which is equal to 41.4%. And it has dropped from I think it was 75.7, if I'm not mistaken. I can check that. What was it again? 75.7. Yeah, 75.7%. And it has dropped to 41.4%. Right? It is an improvement. And now you need to be careful, because we have changed our threshold, right? It affects everything. It just doesn't affect the yes column. It's going to also affect the no column. So you need to balance the two. How did it affect the no column here? This improvement came at a cost, because now 235 people who didn't default are now being predicted to be defaulters. In the previous one we had 104, but now the wrong predictions for the no class, it's now 235. It has increased. It came, so the reducing this threshold came at a cost. It came at that cost, right? So overall error rate now is slightly increased to 3.3%. This is the total or the overall error rate. It increased to 3.73%, right? For a credit card company, what you need to do is to decide whether this cost that you have incurred here, is it worth it? Is it worth it, right? You need to understand, is it worth it? And what someone can do is they can plot the thresholds. They can plot the thresholds, and here they can plot the error rates. You can plot the error rate, right? So when they do that, they can come up with what do you call this? Let's see. What do I want to plot? Okay, I want to plot this. This is going to be my total error rate, right? Total error rate. Let's say here this is going to be 0.5. So that is my total error rate. Total error rate. Total error rate, right? As you can see, when we went to 0.2 threshold, our total error rate slightly increases, right? Slightly increases. Cool. And then here we have this as there. You can have this as there. So this is going to be the error rate among defaulters. Error rate among defaulters. As we decrease the threshold, the error rate among defaulters, like picking this up, it's going to decrease. It's going to decrease, right? It's going to decrease. It's going to decrease. It's going to decrease towards this side as we decrease our threshold. As we decrease our threshold, we are becoming more and more conservative. We're saying if you have 0.1 probability and above, we are already predicting you as a defaulter. So we are picking up more defaulters. So our error rate decreases, right? Cool. Yeah, it's going to be the Bayes one. This is where the Bayes one is, because Bayes uses the threshold of 0.5, and it will have the lowest total error rate. It's going to have the lowest total error rate. Cool. When you extend it to like 0.7, it's going to start increasing like that. It's going to start increasing like that. The skill is identifying which threshold to use, because you have to balance this error rate among defaulters and this total error rate. You have to balance the two. The skill is how do you get the right threshold. And like many people emphasize, you need domain knowledge. You need to know your industry. You need to know what you're building. If you work in the credit industry, you really need to know the things that affect your business, right? You need to know the things that affect the business, things that are important in your business. If you're a doctor, you need to know for diagnosis what factors are very, very important in whatever diagnosis you're going to do, right? It comes with domain knowledge. Machine learning sometimes is an art, especially when picking this type of parameters here. It is an art. The art comes from knowing your business. That's what it does, right? It comes from knowing your business. There's something that we can use to help this process of choosing these error rates and the thresholds, and it's something called the ROC curve. It's called the ROC curve. And this we are going to see in the next video, how it slightly helps us to come up with ideas of this threshold. So stay tuned for that video.